welcome back. Let's continue our investigation of impulse. I'm very excited. I love this section. Okay, so what we're going to do is we're going to do a little bit of an investigation with an egg drop. Now, luckily, I don't have to do this in person because it would just get messy. So I'm not going to suggest you do this at home because it's messy and we don't want to waste eggs. Okay, so this is what we've got. We've got a set of conditions with a whole bunch of egg sizes, and what we're going to look is what happens when we drop the egg through a certain distance and it hits the floor. Basically, what we want to try to do in this is see if we can not break the egg when it hits the floor, okay? I have a small egg, which is going to be dropped from 1 meter, and it's going to hit a hard floor. So let's see what happens. Here's my conditions. I've got an egg of 40 grams. It's dropping 1 meter. It's going to go on a hard floor. We're concerned with the zoom in view, the big block. So let's watch what happens. We drop the egg. It's coming. There we go. There we go. And it's exactly what we expected. The egg broke. So let's just have a look at the information that's given to us. Upon impact, the change in velocity was 4.4 meters per second. This took place over 0.000, that's quick. What happens here, and what we have is the equation for Newton's second law in terms of momentum, is it experienced a force of 44 newtons. The egg broke. Okay? So, let's see if we can change the conditions. Let's keep the small egg. Okay, let's change the surface to 1 inch of foam. So that's 2.5 centimeters. So you can't tell on the TV anyway because it depends on it's about this big in my hands, I think. Not good with distance. And it's foam. So foam's a little softer, right? So what we expect is the egg should take longer to stop. That's what we expect, so let's see if the egg breaks or not. All right, so here we go. There's my little foam at the bottom. Let's see, oops, no, wrong button. There we go, let's drop the egg. Okay. It says the egg's safe, but it still looked like it broke a little. Let's see what was the same. It still changed by the same velocity. It was still going 4.4. The time is now 10 times longer, okay? So it took longer to stop. It now only experiences a force of 4.4, and the egg was safe. It looked a little broken to me, but it's all right. The longer it took to stop, the smaller the force it experienced. The change in momentum is the same. It still hits the foam at 4.4 meters per second, okay? Let's see if instead of the 1.8, we put it in a foam box, okay? Let's see what happens. Big foam box, so if this breaks, then there's a problem. So let's drop the egg, see what happens. It goes into the foam, absolutely safe. Look at the time. Compared to the 1-inch foam, that's double the time period. It now experiences half the force. So force and time are related. They are inversely proportional to each other because the change in momentum is the same. Let's go and let's use a large egg, because we can. Okay, let's drop the large egg from 5 meters and put it on a hard floor. I think we can all make a prediction as to what's going to happen, but let's do it anyway, okay? So we're going to drop the egg. What you're going to see is you're going to see the egg a little bit on the zoom out view. The zoom in view is just the last meter. So here we go. The egg's dropping. We can see it, and here it comes. It very much splashed, okay? Egg very broken. The velocity, 9,9. It took 0,003 seconds to drop and experienced a force of 198 newtons. It's very broken. It's smashed. It's a mess, okay? Let's see. So we saw with the small egg that the 1-inch foam prevented it from breaking, okay? So let's see if that will work with the large egg. So we're going to do it again. Let's see. And there it goes. There it goes. It says the egg is safe. I'm not convinced, but it's all right. What did we do again? We made the time 10 times slower. So this became 10 times smaller. Okay? It took less time, force becomes smaller. Okay? Let's go and do it with the foam. Let's do the foam box. Let's run the trial. Okay? If it was safe on the inch foam, it should be safe on this one. And again, we increased the stopping time, took a lot longer to stop, force is much smaller. The longer it takes to stop, the smaller the force it experiences, okay? Let's see just if this works, if we use the jumbo egg in the foam box, okay? The jumbo egg is 80 grams, so let's drop the egg. It should be safe. What I need you to see, though, is the large egg and the jumbo egg, when it's dropped from 5.5 meters, still hits the ground at 9,9 meters per second. Doesn't matter about its mass. Its mass determines the force. So this one got 13,2 newtons. The force is bigger that it experiences because its mass is bigger, but it still stops in exactly the same time. That's the important thing to get here, that here, the change in momentum is determined by the mass, not the velocity. How long it takes to stop is dependent on what it falls into. So the longer we can take it to stop, the smaller the force it experiences. And that's what we're looking at with impulse, okay? So let's put this into some words. Why is it useful to express impulse in terms of momentum? If we think about this logically, we've said F net delta t equals change in momentum. Change in momentum is much easier to measure. It's easy to measure the change in velocity of an object. It's easy to see the time. So using change in momentum, we can calculate the force that an object experienced. It's exactly what they do when they look at car accidents, and now they're trying to decide, I'm sure you've seen crime scenes shows and all the rest of it, and they're trying to determine what force the impact was. They can calculate the change in momentum, and they can work out what time it took for the force to happen. That way, they then work backwards, and they get the net force that's experienced. And remember, when two objects collide, they both experience the same net force for the same amount of time. Please, Newton's third law can't get thrown out the window in this section, okay? So, during a collision between two objects in an isolated system, both objects experience equal and opposite forces. Why? Newton's third law. Oh, there we go. Newton's third law. Okay, this is what I'm trying to get. So, if I have an object here, and I have an object here, let's call this A, let's call this B. A pushes on B, so this is the force of A on B. B experiences a force on A. Okay, they are both in contact for the same amount of time. Okay, we know that F net, oopsie, no, I'm trying to find it. Okay, we'll just draw it all again. So A, B, we're good with this. Force of A on B, force of B on A, F net, delta T's impulse, okay? Both of these experience the same force, which is F net, for the same amount of time. But one of them has to be negative because we always have to have a positive direction. That can't disappear. So if I make A's direction positive, okay, that means for me that my impulse on A is the negative of the impulse on B. All this means is F net delta T for A is the negative of F net delta T. The only thing that's different is direction. What we may find is that the objects don't have the same change in velocity because their masses are different. That's important to get here. Just because F net and delta T are equal does not mean that they change their velocity by the same amount. Their total momentum will change by the same amount, but not necessarily the velocity. It's mass dependent, okay? So, now, we've looked at it. We've realized that F net delta T can be affected by time. And when we want to make the net force smaller, we have to make Ft bigger. We are going to look at that again in detail. But F net delta T equals change in momentum. And when two objects collide, they experience the same net force in opposite directions. So they have the same impulse, just in opposite directions, which means both objects experience the same change in momentum. I'm saying the same thing over and over again because it's important. Now you're going to take a short break and you're going to think through what we just did, and then we'll do some problems. I'll see you in a couple of minutes.